Добрый день. Еще раз меня слышно?
Can you hear me? And probably, will you please demonstrate my presentation on the screen? I would like to start with a part that is not quite technical. There was one TV program, and my competitor said, I would like to give best regards, and I would like to give best regards to my son, who is 4 years old today, and to my spouse, who will just pardon me that I am not with my family, but I am among you, and probably it will be beneficial. Well, what are we going to discuss today? We're going to discuss the specific feature of development software for multi-core systems. I would like to stress that we're going to discuss three cases which do not differ significantly from desktops, laptops, servers, or mobile devices. But in case of bigger devices, we know why we need multi-core systems, but we don't know how to live with it, though the approaches are the same. As to embedded, we don't understand why it is needed. We speak about portable devices such as trackers, such as reindeer trackers and other devices. All these might be parts of more complex but portable devices such as phones, but this will be a bit later. I will tell you a few words about myself so that you would understand the context of what I know. I work at Synopsys company. I have been working for more than 10 years. I have been developing software for microcontrollers of different families with ARC architecture. So we started with a simple 32-bit, and now these are multi-core processors. Yesterday I learned on Open Hub about myself. If you haven't yet registered, please register. It is interesting to analyze the statistics. At least I was interested. And a lot of time was spent to porting of EVOOT, the core of the operation system of Linux kernel and other systems. Lately I started to engage in Zephyr, and thus I can make a presentation about it. So what are we going to discuss today? First we are going to examine the user cases for multi-core embedded processors. Then we're going to consider two main options of implementation of multi-core processors, symmetric and asymmetric. We'll start with asymmetric as a more common space. Then separately we're going to discuss what are the challenges or specific features of working with SMP system and Zephyr, and how Zephyr can use it and how it is realized. Then we're going to discuss the very interesting and simple part that could be the heading of my presentation. And first I wanted to discuss SMP and see how we can add hundreds of cores that will be more efficient, but we'll come to it afterwards. Why go multi-core? The more resources, you never have more money or disks or megahertz. As soon as we have resources, we try to use all the resources. Up to some time, we can just increase the velocity of operation of one device, one calculator, one computing device. Then, for instance, if it is a portable device, if it is not an advanced device, that might be even hundreds of megahertz, and that will lack it. And besides, when we increase the frequency, energy consumption would increase not in the same proportion in which we increase megahertz. And we're speaking about portable devices that should consume moderate power and operate at least during the light day, or in point in St. Petersburg, 2 or 3 hours would be enough. So we understand that we have to do with something, with this something, and we can add to one a computer, the same one, and have a double budget in megahertz. We can have 2, 4 or more clusters, but that is not an embedded solution. But there is a possibility, which I'll show in the next slide. Another interesting application of multi-core processor. Some operations might be quite specific. For instance, processing video or sound and work with neuronal networks. You might use a common general purpose calculator, but for one iteration of computation, too much energy and time will be spent, and we can add a coprocessor that will process certain data and make certain operations, and that will be done quickly and efficiently, and we'll have to interact with it. These are the problems which you have. What are the solutions? I have already mentioned. We use processor cores, or we use the cores that make it possible to speed up the process. And we have a funny story when we have a lot of similar cores. That guy in the white helmet is the master core, and the solution that we can use to add cores, similar cores or other cores. What are the examples of multi-core solutions? What are the use cases? A popular use case is LTE modem. My colleagues from the companies that are developing Aurora OS modem is an interesting thing because it transmits data. Using modem, you can also have voice communication, and we don't want, when we have intense data exchange, not to be able to talk, or vice versa. So for this, we probably would like to have that thread of processing sound system, sound information to be on a simple core, and thus will reduce latency and solve some other problems. As to LTE, if we are not speaking about neural band that can operate on several megahertz, for full-fledged LTE, we need a lot of calculations, this calculation-specific mathematics and controls tech. Thus, we have to have a lot of computational resources, and we have a possibility to control them flexibly. As far as I know, the advanced LTE modems are based on multi-core systems. And what I'm going to talk about is applicable for them. Another typical use case, processing of audio and video. We're working with data blocks and work with them cyclically. Similarly, so for audio, we use cyclic buffers, and the architecture of the process for video disk, we can use vector instructions so that simultaneously will process certain blocks, so repeat a digital operation in one block. As to the artificial tasks related with artificial intelligence and with revealing and processing of video, the same story. We need CNN engines. These are very powerful digit splitters containing a lot of multipliers, and we cannot use a common processor, otherwise we'll spend too much time without doing anything else. Besides, we might have some complex devices where we have to have the user interface and to have the response of interface and the possibility to take and control the periphery. With what we started, probably once we have an 8-bit microcontroller, then 16 and 32-bit, but that was not enough, and we have produced this cluster that comprises several units. That is interesting. And then we decided that it would be good if the processor wouldn't operate always, so that it will be switched off when we are listening to music in the street, and that will be data will be sent toward the output. We decided to use mailbox, proprietary, for interacting between our master co-host cluster and our coprocessor. And then we decided that when we are not listening to the music, we would be measuring our steps, and we we introduced a more lightweight core that can just ask one sensor and send interrupts when interesting information is ready to our master core. And using the camera, we have to recognize some pictures with minimum energy consumption and quickly in real-time mode, so that it would recognize a lot of objects in the picture. And we added a powerful processor for processing of pictures. We decided to communicate it through common memory with host processors, through shared memory. Thus, we have a whole zoo of different processor cores. You shouldn't be surprised that there is ARC, that might be ARM or whatever. Since we work at Synopsys company, we have a portfolio of processors covering it. But as an example, I use what I know well enough. We had to live with that zoo. We can classify that zoo, and we can distinguish a cluster. For instance, the cluster that I would call asymmetric multiprocessor system. That is a common case. We could also combine these two processors or any other processors. This is a common cluster, and we have NCP cluster that also has specific features. That is a private case to ENP that satisfies certain criteria, and we are going to discuss it now. So what is ENP asymmetric multiprocessing? We have two different cores. These might be cores of the same architecture, different architecture. These might be not necessarily the core of the processor as we know it. That might be some FPGA with its firmware or whatever. And each of them has its own software, performance programs. That might be an OS, that might be a bare metal application, even FPGA. The specificity is such that there are a lot of specific features or no specific features. Any two processors operating together on one SoC can be called this asymmetric multiprocessor system. However, as a rule, when we developed the software, we are interested in having some interaction between these two executors. Though I know that there are use cases in real life which represent two independent program steps that don't know anything about oneself, that is not flexible and efficient, so some interrelations should be established. In case of a system when the design might be quite different, these might be different cores that have access to different peripherals. They might have some communication or no communication channels. From the communication channels that they can be used with, that is a common area of memory, the simplest one. It is not always available. One of the cores can use its internal quick memory and without access to the external memory. It is not always simple or free of charge. In terms of additional logic to our tip and additional expenses on the area, production and overhead of productivity. The next thing that is used extensively, I know that in AMX processors, which you are actively using, in AMX proprietary mailboxes are used that are necessary for interaction between the cores. I didn't use them. I don't know what is the advantage of these mailboxes. Probably some other things do not work. A larger core communicates by mailbox. Often we see a cross-core interrupt. So one core can initiate interrupts that the other processor would see. That doesn't always exist. It is present or absent in certain designs. We can use or cannot use it. And interrupts can be just interrupt, but by some additional information. Transmitting interrupt interrupts, we might give the indication to the function to be performed or some data related with the interrupt. But it is not precise because it might be realized in different ways, or probably these might be some hardware semaphores. As to the software development, since if there are different cores, we won't be able to launch what we have collected on that core, on this core, because they have different architectures, memory in different ways. So developing software, we have to develop into part working on one core and the other core.
It's good and it's bad at the same time. We can predict different things, but we should prior decide how we're going to partition it all. And also, thanks to the fact that this design is very complex and sophisticated and specific, we cannot add up one more core right here, and even without reassembling, everything will be working. We should not think that, because we should figure out which part of software should be shifted onto another core. We'll have to think once again which interfaces to use, how to implement it all. Another option, which is a subset of the entire diversity of imperial solutions, is symmetric multiprocessing. It's a very symmetric system. This core and this core are very much alike, but they should be identical from the standpoint of software. They should not be absolutely identical from the standpoint of hardware. If I refer to broadly used architecture, big literal of ARM company, there could be cluster with 4 cores, high productivity, and 4 cores of low productivity. They could be within this concept of SMB because they are binary. In a binary way, they are compatible, have access to the same periphery, so we might consider that it's symmetric multiprocessing, although there are slight differences. Nonetheless, if those cores are identical, have access to the same periphery and to the same memory, we can assume that they exercise one and the same program code, one and the same binary. Each one, on the one hand, implements that source code and file, but each one performs a certain part of this payload. This system is such that we perceive it as multiplied by 2, one universal digital system multiplied by 2. That way we can implement this partition of tasks between the cores, not in the process of software development, but to allow a program mechanism, which is called planner, to decide it, or prompting it in which moment in time which task should be launched. It's convenient. We could be more flexible, but we are losing hold of predictability. But of course, we can set it a tune, and we should tell Shader that we should use this task here and there. So actually, it's shared memory, like I say, and somebody worked at the low level with the hardware when the task is shifted from one processor to another. Oftentimes entails loss of productivity because there are caches used in contemporary cores, lots of caches. We have got obvious caches and of data and caches of instructions, and we have got caches of the system of memory operations. If we use MEMU, I'm talking about TLB, we have got branch predictor caches, which is non-static, and it memorizes in which places and which way the transitions were made. We're losing that as well. And some other states. We remember when we shifted to a new core, all the information we were compiling, we'll have to compile it again, which will bring about delays in performance and execution. But this solution has got a very good advantage. Its scalability, its complex runtime scheduling, and it's scalable. So just add another core in cluster, and you'll increase performance manifold. and it really works. But for this system to work smoothly, there is a set of requirements for that. We need shared memory they're going to use. If we have got caches, they should be coherent. Otherwise, an operation with data which is used by all the cores or by some of those cores will require the data being shifted to memory, and then cache lines should be retrieved. That will kill productivity. So it's a must to have coherent caches, and there could be also cross-core interrupts because it reduces delays and simplifies the work when we have to inform another core. Talking about hardware, why do we bring it up at software conference, and how is it related to Zephyr? Zephyr is interesting for us to simplify our work in development of software because Zephyr provides us with support of a big number of peripherals, different support, subsystems support, and we can use the abstractions of threads and processing. We can create two threads, launch them. Each one will be given one quant of time, and they will be launching. This is very convenient, and it's peripherals abstraction and it's complex subsystems. This is convenient doing it like this. As to Zephyr, Zephyr and AMP and Zephyr. Since the first Zephyr public release, AMP was supported, was working on the CPU board beginning from release 2, was removed. Intel lost interest to this platform, but there was that platform, Arduino 101 with Intel Quark SC, so continued 2 cores into x86 core and ARC EM4 core by Synopsys. It worked in a very simple way. For each core, we were assembling our Zephyr core, exercising them useful work. The only way of communications which were available, it was a small area of shared memory seen from both sides, and those registers actually RCM start-stop signals via quarks SS. CFS regimes. That way, this is a customized way of interactions. It was implemented, and we had a full-fledged IP system. Currently, Zephyr supports some other development platforms, which also consist of 2 cores at least, having some differences. It's exactly the case when SMB will not be working, and AMP could be on those platforms, and it will work smoothly, and this platform is most supported of all. Now, for you to understand how simple it was to implement, here is the bit of a part of the code, initialization code for Intel platform. This is for ARC. Everything which was happening in case of x86, we were computing the state. We launched the ARC processor. Then we were waiting for it to start, and ARC processor was exercising very simple function here at start. They were inserting the flag into some structure of shared memory, and then they could go apart and do their own chores, each one. The simplest application didn't envisage any other dependencies. Even using these IPC mechanisms, we could come up with more interesting things. Speaking about more famous things which you can do on an AMP system, there is the project which is called Open AMP and Zephyr. It's an attempt to standardize interactions in HMP systems between the cores within one AMP system. system. What is it all about? It's the project which suggests using several standalone components. Altogether, they implement a full-fledged and smooth work of the system. What are the parts of the system? First one is lifecycle management part, which is there for us at remote, so that at remote core we could stop and start, launch and relaunch something, thus managing the software lifecycle from the car. Secondly, it's IPC mechanism, it's inter-processor communications to use for data sharing. That's what we need. And all of this works on top of Virtual. This is a transport abstraction layer. We know this protocol is very handy to use in virtualization. It was conceived for virtualization, and it supports from the very start the general memory. It can use interrupts, and it's the abstraction layer. It's platform independent. To have more platform-specific things, for that there's HALs, libmetal, all the architecture-specific things could be there. It's hardware abstraction layer. All the three components over there are platform independent and could be reused, which is very convenient, and we use it broadly in Zephyr. Here you can see the diagrams as how it all works. It virtually is working. Two queues are there, one from host to slave, or host to coprocessor, and second queue coprocessor to host. We compile data signal that they are available and move it to the other side. The other side does something with it. OpenAMP currently is supported in Linux and supported by different RTOS, free RTOS, Notefix, Zephyr, and bare metal. You can use it as a library. As to Zephyr, it's only now for NXP LPC 54114. At least for this PCU, you can do it. At ARC PCUs, we don't have it, but recently they will be there. And if you're interested, you can check out the presentation which was made on Linux Connect in 2018. There are more information about Zephyr and how it works. Another thing is it's a truncated version of OpenAMP. There is no lifecycle management part, and it's the mechanism of sharing data between slave core and master core, not just for Zephyr only. In Zephyr you can use external library, which is supported by Zephyr. The project is supported by NXP guys. Currently just supported. It's not very good that, unlike OpenIP, it's not community yet, but it's supported by one person, one man only, but it exists, and at very restricted platforms it's possible to use it in a very good way. Why cannot we use that as a universal way? Because actually sometimes it's not, there will be not enough resources to allocate in memory all the interface resources, and actually as to RPMC Lite for devices with limited resources, and it's smaller code size first of all, and we use dedicated buffers. We don't copy into the buffer. Master places the data there, and slave reads and process them from the buffer. We don't have to have more copying. We reduce memory, which is needed. Everybody is happy, but it makes the system less flexible, but sometimes there is no other way around. As to SMP, it came along much later than NLP. AP was in the first commit, and this one is since February 2017, because it requires OS-wide support. That's only emerging later. As to February 2018, its initial support with ESP32 and version 1.11. At ESP, there are two cores, very magic key, but we cannot interrupt them easily, which brings about longer delays in order to implement a signal between the cores. What can we do? Sooner or later, we hope one of the cores will finish the current task. We're talking about RTOS. And between the shifts from one task to another, we'll check up whether some messages came along from another core. These will go till infinity. We'll never know that we should drop performance of this task and get switched to something more important. These are the limitations. Much later on, a year after the first support of SP was merged in Zephyr, there came along the support of SMP for JSX 86, so the added X86 and 64 in version 1.14 in February 2019. So the platform which doesn't require any hardware for releasing and launching an adjustment of the entire SMP structure and application. And here came the next support. Quite recently there was support, and I'm very proud to say that it's a full-fledged support of SP for architecture and for our development platform and for our simulator. It's much better because in our case there are inter-kernel cross interrupts, so we can control latency when it's necessary to transmit a message from one core to another. So what do we have here in Zephyr? What can Zephyr do for SMP? Current status, shared memory, cross-core interruptions, if there is the source of information which is available for all the cores, we can simplify working with time. Each core can receive the information which time it is, what time lapse since the previous moment, which is very important and very convenient. It's cluster-wise wall clock, and also there should be hardware atomic instructions. Otherwise, it will be very difficult to implement those primitives such as spin locks if access to atomic instructions will not be there, so it will be a failure of the system. Another interesting feature which showed up recently, now it is possible to just connect some tests to this or that processor core. Will retain caches on this core. It's very useful, but not always needed, because in case of RTOS, we can guarantee whenever it's necessary to have a launch task at one of the cores till just infinitely. With Linux, it's not possible. Sooner or later, all the tasks will be given their own time quant, and in Zephyr case, like RTOS, we can retain one of the tasks running on one of the cores. It will not be tied to core because it will be there until we're interested in this task. Nonetheless, as SMP support is at very preliminary stage, we have lots of things to develop. Only 3 architectures support SMP, and only SP extension ARC are used. X86 is there just to play around with this on your computer with all those SMPs. ARM, ASC5, you name it, and other architectures will have to add it up, add them up. I think the hardware is available, but someone will do it. Maybe guys from Intel, maybe guys who are supporting those architectures. Who knows? It would be interesting to add more tests and benchmarks. We'll speak about it as well, because there are rather straightforward applications which show us that there are launches of different threads on different kernels, different cores, and they are exchanging information, but that's very simple. We want to have something more sophisticated to figure out how it really works and to demonstrate better opportunities. Nowadays, mindful of a limited number of platforms to be supported by SMP, at configuration we can see that there will be up to 4 cores, 1, 2, 3, or 4, but no more than that. It's not fundamental limitation. It's related to the fact that we'll have to slightly rewrite the code in order to have as many cores we want, or to add up in the moment when we need 6 cores. Let's see what else will be done. We'll have to slightly improve the scheduler so that it will take into account those cause extra costs when we shift the task from one core to another. Even if we don't do it in reality, it should not be done. But when the task was first done on one core and then it was scheduled for another one because it was the time has come, it was to be executed. So there should be a fancier schedule, and so we should take into account the CPU migration costs. So actually, Linux operational system is using that, but actually it's also we're at the inception stage here, and what we lack yet is S&P aware Zephyr debugging with OpenOCD, GDB, adjustment of Zephyr in OpenOCD, GDB is existing, but it's not in full swing. There are no bottlenecks here, but we should develop more OpenOCD so that it will be able to find information about threads. Now we have got one task launched, and we are able to read its state from the registers and retrieve all the other tasks from T-specific structures via global structures. They are available, but with SSP there will be several concurrently executed threads of information.
And some amount, certain improvements should be made as well. Now, a few words about the technical characteristics. Probably someone might be interested why the support of SMP didn't appear immediately. First, Zephyr was non-mature and young. There were other problems which we had to tackle. Even coming back to AMP, it can be resolved using some platform-specific additions here and there, as we added the codes without touching the OC, and there was a working interaction between the cores. In case with SMP that is not the case, we have to do some additional work. We have to initialize our slave cores. Master core had to be initialized because without it, it wouldn't work. Now we have to initialize slave cores because probably they didn't perform any useful work at the time of the start. We want to stop if they were running. We want to have some initial adjustment or tuning by our host or master core, and then launch our pre-adjusted cores that will interact with the master core. Those we speak about symmetric multiprocessing at the early stage of bugging. It isn't symmetric. Master cores starts the slave cores, and only the work continues. There is no master, and all the cores are equal. We also had to do the following. In case of a single core system, in order to avoid the possibility of getting to the same code two times, we have to prohibit interrupt. Otherwise, we execute the code. With SMP system, that is not the case. We execute one code with one core, and we could get into the same code by executing the core on the code on the same core. So we should not only prohibit by prohibiting the interrupt, we have to add a certain spin lock. All the places that were used. First we had to use add the realization of that global spin lock, and we had also to make refactoring of the code. For instance, we had to change the code of switching the task, because previously we just switched off the interrupt, even in architectural specific code that can be done by one command. If we have to realize spin lock, that code should be not left in the parts that are written for architecture platforms. Is not a good idea, because that is a more complicated task. There will be more problems and errors, and it will be difficult to resolve it. Besides, we have to remake the planner. Previously, we had the queue. The first very important task was to execute, and after that the next task was executed with the second priority. When we have several executors, we have to use several threads to be executed, and we should be ready for switching. We have to think about the next 4 tasks. If we have 4 cores, we'll be sent to what cores if there is a necessity to switch off the contacts. That makes it more complicated, but we are doing it not on architecture specific level. We are doing it once and forever for everyone. And then all those who have the support of SMP can write a small code. Arch switch is realized instead of swap, then we can easily use all the advantages. Now, coming back to the requirements for hardware for SMP, so that we could launch this beautiful SMP software. First, this should be at least binary compatible processors. In this case, we have 2 similar processors. That is the simplest case, but it is not unique. Then we need shared memory. There is an interesting thing, because modern processors, particularly for embedded applications, have a possibility or inbuilt quick memory on the chip. And its advantage is that, unlike the external memory that might have delays for access, or about tens or hundreds of tags. Thus, we have several levels of cache. Having the on-chip internal memory, we can address it quite quickly as to the cache data, having a delay of 1 or 2 tags. But quite often this memory can be private. It is accessible only for this core. For instance, this core can give the data, get the data from here, or this cannot do it only through a certain interface with external access. If we read by address 0x, when this core will see this memory and that core will read this memory, will read different data. In this case, the idea of SMP is that we use common data. We have certain variable that contains the values 1, and we should have a possibility to read that value similarly by all cores. We might think that we have logged that primitive, and here we won't see the change, and we'll come to the critical section seeing an interesting behavior. We have to have a possibility to send interrupt from one core to another inter-core interrupt unit. And in our case, it is good that we have a multiplex of interrupts that can be adjusted to work in the following way. Each interrupt that flies to it is sent to the next core, so we have 4 cores. It will be going to the first, second, third, or fourth, or each external interrupt from USB will be routed here. That might be quite convenient and add flexibility. As to the memory, in case of architecture processors, there is a quick memory on the crystal, but it is accessible to all the cores. Such memory can be used to realization of SMP. In our case, when it might be several megabytes, in the simplest case there will be 128, 256, and 512. That will be enough for Zephyr for the code or data. As to the internal memory, which is accessible only to one specific core, it is not RISC, or RISC-V has a similar memory, so probably we shouldn't get code and data in SMP there. As to the challenges that occur during designing and use of SMP-aware software, first in Zephyr we have several options of the logic of the work of scheduler. This might be a simple version when you have a queue. That might be a time-sorted queue. That might be a red and black tree or some other mechanism, and even the simplest schedule, the so-called DEM scheduler, allows attaching tasks to each core. Sometimes probably it is not necessary, because if we have a queue with a high priority, then we don't need any attachment. A very important challenge or some specific feature might be related to work with resources which are in one copy. For instance, the source of time, clock source. If it is necessary to make some operations with our peripherals, we have a serial port 1, its register is in one copy. If two cores write to that register, there might be a mixture instead of a good log. So in order to overcome these challenges, we have to add CC realization, and our critical sections are surrounded by logs, and this time period when the log is on, there might be a situation when one core performs the code in critical section and the other core is waiting. We'll lose megahertz of the generator that might do some useful work, and we have to wait. Besides, the code increases and the execution of the code increases when we add additional software and hardware barriers. The execution of code in a pipeline might change. There might be reordering of the structure that would speed up otherwise our work, or reordering doesn't take place by means of the compiler. But probably it is not obvious why we have caches here. We have cache of the second and third line that is common between cores. If we want to make some operation from one core, for instance, to analyze all the cache lines available, or to bring to the memory the content of the cache, we'll do it from several cores with time overlap. My one core would set flash the entire cache, and I said we'll say different way. Probably the devices can do it or not, so we have to do it in a good way, but that means additional expenses. As to the use of SMP in Zephyr, in order to include support of SMP for the platform for which SMP support is available, and the architecture should support SMP, we are going to the utility of configuration vconfig, kconfig. We go to the core. We say that we want SMP use, and there are 4 rows that we can use in that cluster, and the output will have a binary that we are going to execute on our devices. Besides, some examples which are targeted at testing SMP include that option, and that option will be switched on even if it wasn't included into the configuration of our board. So what can be seen, how it works? Yes, examples and benchmarks are not sufficient. We have to write our own examples. I just wanted to count P in many flows. P is counted in each flow from the beginning to the end entirely with an assigned precision, and thus I wanted to simulate the computation of computation-intensive tasks that will be shared in many flows and many times, and use all the computational resources available. And thus we might see what is the real benefit, what are the advantages if we can use the system where we have several computators instead of one. We create several threads, and on each thread we perform the task which uses in simple calculations computations P number. If the precision is 240 symbols, we have linear scaling. If there are 4 processes, the acceleration would be 3.5-fold. Probably SMP makes it possible to get scaling similar to what we expect. However, if we shorten the time in each particular thread and we count only 120 symbols, scaling will be different. At best, test will have it 2.5 volt and 4D. Where are the cores? Where are the megahertz? If we analyze the more extreme case, which we can see launching an interesting test, we take a picture and by lines we are turning it using all the cores that we have. In this case, we can see that even the increase, twofold increase of productivity would not be attained, because since we are reading from the same file by several flows, most of the time is spent in waiting when the indicator is free for that part of the data which we have to read, because one core reads and performs operations that is needed, and the second core has blocked access to the indicator, then it is freed, and they are waiting for each other. And in some cases where the data are interrelated, between the processes, we might not have a good scaling as we expected. And probably it would be more efficient to give a picture on one core. We might have even higher efficiency than several cores. We didn't have to realize that semaphore. We have one process and we read as quickly as we need. We shouldn't block in this place, so we shouldn't switch off the interrupt to make some operations. We might read and transform further. So what I wanted to give in my presentation, Zephyr means available in the current OC, make it possible to realize the efficient uses of multi-core systems in the equipment, irrespective of the architecture of the devices used. We can support composite heterogeneous systems that comprise SMP cluster and segregated cores. For SMP cluster, we can use SMP because there is a good support. For MP approach, we can use OpenMP or our own MP in cases when SMP cannot be launched. And probably it is not interesting for those who develop software. If there is a possibility, you have to work with your developers of hardware, so when they are developing hardware, they would know what software will be used and what are the requirements of the software to the hardware, because in the chip, for instance, extensor, we added an interrupt, and it would be more, SMP platform would be more attractive, and here we had to use what was available, and it would be good if what is planned to use, the possibilities that are planned to use in terms of the hardware, it would be good if these components are supported by the software. It would be simpler to change the hardware before taking the decision and providing a mini circuit, then solving the problem related to the software, remaking of generic infrastructure or drivers. It would be better to think before the hardware is ready. And the last item that is important, use of SMP system in certain cases gives a significant increase of productivity, and we can get a virtual increase of the number of parrots and the number of additional cores, but that is not always dependent on the use case. Productivity might grow, but not to that extent. And to conclude, since the Zephyr project was discussed previously by Andrei, that is a project with a very rich open source project with a very pleasant and rich community. So we'll be happy to see you among those who report among the problems, those who contribute the amendments and improvements. We are happy to meet you and to receive your help. Thank you very much. That's all was that I wanted to tell you today. I'll answer questions if I have any. Was it too simple or too complicated, or probably have you fallen asleep? My question is, are you planning to support SMP on ARM architecture? This is not a correct question. That is the wrong person whom you are asking. I'm at Synopsys company, and my working time is paid for ensuring better support of our architecture, not the architecture of the competing company on the market of deeply embedded systems. Even if I knew, I wouldn't tell you, but I wouldn't do it. That will be done, there is no doubt. You have to understand that the community and the number of people who are using ARM cores and decisions is quite significant. Why hasn't it hasn't yet been done? That is quite enigmatic. Probably the ecosystem is so rich that by inertia people use NATX and some other OC of real-time. With that, we have a support of SAP in ThreadX, and in Zephyr no other options are available. As to the OpenAMP, it also supports other OC of real-time. Probably time has not yet come. I think that it will happen in the near future. Since there are a few actions that have to be made for that, why not experimenting in during your leisure time? I don't have any boards except Raspberry Pi, though could also be done Raspberry Pi. Thank you. Another question, 2 or 3 questions. You have awakened. I have a short question. Aren't you afraid of risk 5? I would discuss it unofficially, not because I'm afraid to answer the questions, but that needs a lengthy discussion. No, we are not afraid, and there is a good reason for that. Thank you very much for your interesting presentation. Some words about the mechanism of adjustment and profiling for the open AMP. What specifically, for instance, if we have a certain task which we have to solve to get some time characteristics for this task, certain cycles or adjustment that is done by some means. What means are available? The simple thing is, since we have a powerful system of logging, that is not a printer, that is a extensive system of...
It's a full-fledged logging system. Instead of introducing low port, we can log it into the memory, and then we'll retrieve it when we need it, so it will be a very good time log. If you need more hardcore things, you have got timers, infrastructure, measure times, calculate, process, or show them. There is no golden rule or super instrument to tell you whether OpenMP is working in the right way or not. It's just a lib. It's a library you can use, and then depends on what you need. Yes, I've got it. Thank you. I don't see any more raised hands, although initially there were more. Yes, there is a question. There is a question. I just... my question is, you mentioned that there are instruments for anti-bug and debugging systems, but some is yet missing. What else do you need? What did you lack? I was not talking about adjustment tools. I was talking about tests and benchmarks. I was surprised to see that it's good if we can be convinced that SMP is working in a very good way. There are lots of different tests which show us that everything is working. But in the case of SMP, we couldn't actually evaluate it initially. You can have a 100 core system, but if it does not increase your performance and all the time will be glued to the planner, maybe it's to the schedule, it's not the best way. So I had to write down my straightforward benchmark or test which shows if there's no strong correlation between the data and our threads, then we can get very good scaling. Such things are missing actually. We lack that. you might be interested to know which lags are there, which delays will be there if we reswitch. In my text, like in Linux example, I'll show what happens when we have got very strong interlinks between the tasks. We spend a lot of time to reswitch from one task to another. Time of reswitch is very important. So tasks are replanned and rescheduled to different cores. It's interesting, we should do that, but we didn't yet because SMP is quite a new thing in Zephyr. Thank you very much to the speaker.